Okay, so this video is about the start of the problem of consensus. So we've covered link timestamp, we've covered proof of work. They're going to blend a little bit back into the consensus topic later, but right now we're starting here, and this was when the consensus problem was defined, and marked the start of a series of trials, efforts, failures, discovering new problems, new solutions, all trying to solve the problem of consensus. But we're going to start at the very beginning. and Bitcoin is a solution to the consensus problem. But over the next few lessons, we're going to understand deeply the problem of consensus, and knowing the ins and outs and different angles of this problem is a key piece to understanding how Bitcoin works and how Bitcoin solves it. So that's the definition of consensus. And we're going to start with an example. So in the 1980s, this is still the dawn of the internet era, and this also overlaps with the Cold War. The United States had a distributed computer system consisting of radars, missile sites, Air Force bases, command and control centers, and so on, all in the name of protecting the mainland from Soviet bombers. This is a Soviet bomber. And we had these radar displays at each site, but we're just going to start with the radar in Alaska. So it's in the state of Alaska, and it's going to send its raw data to the other locations. So each location is viewing the Alaska radar site. And then geographically, this was the line between the United States and the Soviets. And there's a better way of looking at it. So we have the radar dish in Alaska, and then each location, Hawaii, Alaska, North Dakota, Virginia. This is kind of the line that was against the Soviets. All of these places are going to be able to look at, see the same data coming out of Alaska. And the redundancy here is intentional. And this was in case that one of the sites got bombed by the Soviets, or maybe it was just lost power or down for bad weather. The redundancy was intentional. And from an operational point of view, we've got this radar site here. It's collecting this data, and it's going to send it to each of the 4 sites. So the data is traveling, and whatever path it has to travel, it's going to go to each of the 4 sites, and so on. So we end up with this, and once the data arrives, each site is going to take it in. And then each site computer is going to update their radar screen based on the data they have. So we'll do an example. So here's the initial state, and they're showing nothing on the radar. And now the radar does detect something. You see this red blip here in the top. And this data is going to flow to each of the 4 sites. And now the computer at each one of these sites has to go through some process to update from the initial state to this new state where it's got the correct blip on display. So now we get to the problem, because it's possible, first, if you look at just this part of the equation where the data is being sent, there are a number of things that can go wrong in this phase. And these are just a couple of examples. Here the line of communication could be cut or fail, or otherwise the message does not arrive to Hawaii. Or here, somehow it could get messed up, or during transit, all you need is 1 bit change from a 0 to 1, and the results, this puts the radar blip in a completely different direction, and so on. Any type of error could happen in that, and it's just not going to work. So if you look at this from an operational point of view, if we don't have this agreement, even this mock trivial example, just imagine for a second you're in North Dakota, and out of nowhere this blip shows up, and it's showing over the state of Texas or something, and they're all going to start freaking out. Whereas if you're sitting in Anchorage, you know that this blip's actually over Siberia, so it's not really a threat. But now North Dakota is going to be calling everybody, and then up and down their chain of command, then Anchorage is going to wonder, well, is my data incorrect? And then everyone's going to be basically wasting all their time, and it's just going to be sheer confusion. So you have to have this correct common picture between all locations when you have this redundancy built in. So now this opens up the second part of the problem. Is we're going to go through this phase here where these all these different nodes are going to cooperate, send messages back and forth, and this opens up just a whole new slew of problems. And one is we can't have a, one of the problems is we can't have a leader. So we can't all just default to what Hawaii is telling us. What if Hawaii fails and sends bad data, or just loses electricity, or gets hit with a bomb? So there cannot be any hierarchies or totem poles. Each one of these nodes has to be equal. And then when they're sending messages back and forth, when they're cooperating as equal peers, again, we can have failed deliveries, or messages could get changed somehow. This opens up this whole new slew of problems. But now we get to the most noteworthy problem. This is considered the broadest, most difficult problem to overcome, and that's this situation where we have a node that's failing at some point in this process, and as it's failing, it's going to send bad data, but it sends different bad data to different locations. That's considered, this scenario is considered possible, and it's also considered worst case scenario. So not only are we leaderless, but we also can't trust each other. We can't trust that a node is going to send us the right data. And so lastly, each node has to know when it itself has the correct new data, and it also has to know when all the other nodes have the correct new data. It has to know when the whole team of nodes here or they have the shared awareness that they all are in agreement, and that they have the correct agreement. And so why when we reach the point of shared awareness and correct agreement, that's one data point, and that means that, okay, we're good on this data point. Now we can go and collect the next one. And the idea of distributed consensus is that, we come to a stop in the process. We're in agreement, we're correct, we have shared awareness. Now we restart the process again, and over time we're all going to stay in sync. And say, for example, also that this node has some kind of failure or issue, otherwise failed at that point. By staying in sync, it's a simple exercise. It's a simple exercise just to repopulate any prior data that is missing. And so this is what the problem of distributed consensus entails. We may have bad or faulty inputs, and then we go through this process to cooperate together. There's no leaders, we can't trust each other, and we have about the broadest possible definition of things that can go wrong that we have to account for. So that's what this problem is talking about, is how do we stay in consensus given all of these challenges? And this is also called the Byzantine generals problem, and it's called this because it's the Byzantine generals problem is an analogy that talks about everything we just covered, but it presents it a little differently. They're talking about the exact same thing. So instead of arbitrary issues, nodes are referred to as traitors when they fail, and it's not nodes. Each node is referred to as a general. And generals are going to send runners back and forth, like oral messages via runners, so they can communicate. And what they're trying to reach agreement on is they've surrounded a town, and are we going to attack this town, or are we going to retreat? And the problem they have is one of these guys could be a traitor. He could send wrong information to another general, and he could send different wrong information, or their messages could get intercepted or lost. It's all the same problems. You get the wrong information. And this analogy was published in 1982. There was actually a lot of negative feedback on this analogy, that people were saying that the author was just overcomplicating the description of the problem. And nowadays, you're going to see more visuals that look like this, which I think this is a little simpler way of understanding the problem. But nonetheless, this name stuck, and these two are talking about the same thing, and you're going to hear this referred to as the Byzantine generals problem. And Byzantine means basically that anything wrong can go happen. So how do you reach distributed consensus given anything at all can go wrong? Now, in the paper from 1982 that described the problem also proposed a solution to the problem. It was a theoretical solution, but it's helpful to look into it. So we're going to do just that. And here's what the solution was. So the idea was that you have one node in the first round. It's going to take the data that it has, and it's going to send its data to all the other nodes, just directly send it to it. And then when the other nodes receive that, they're going to echo that data back to each other. Not back to the original one, just back to the remaining. They're just going to echo it back to each other. And at the end of round one, these are the values that each node is going to have. And now we start a second round. And now, in this case, it's Hawaii's turn. He's going to send out the value that he has to all of his teammates. All of his teammates are going to receive it. They're going to echo it to each other, again, except for Hawaii. And this process is going to repeat 4 times. So 4 nodes repeats 1 time for each node. And here's what the data points look like at the end of this. Is all the data values. And this looks like a ton of random, green dots. And we're going to get into now, why do we have all of these green dots? So let's go back again to all the problems that can happen. And again, the worst problem is this. If you have a fault that happens and it sends different wrong data to 2 different nodes. So Virginia's got wrong data, sends it erroneously, sends wrong data to 2 different nodes. If you can solve for this issue, as you can see for a second, then any other problem that might happen is not as bad as that. You're also going to be able to solve for that. So let's build a solution that can solve just for this issue. So now going back to where we started, so we're looking at a situation, worst case scenario. And North Dakota has a problem. Doesn't matter how it happened, bad data or crashing, doesn't matter. It's giving us our worst case scenario. It's in the process of failing, and it's going to send the wrong radar blip out to different people, out to just everybody. It's sending wrong data to everybody. And if you look at it from a data values point of view, this bad value finds its way all over this map. And not only is it sent directly, it's also sent via echo. So all these faulty values also, this value might even be different than this value, which could be different than that value. Anything in red here could be different. Not only is it wrong, it could be different than the other red value. And we're talking, is worst case scenario. So let's start by looking at the situation just from the Anchorage point of view. So Anchorage has these correct values. It knows what it has, and it knows what Hawaii and Virginia sent it were echoed, and it's also got all of these faulty values. So now we're going to bring in the end state. Okay, changing the slide up a little bit. So let's look at what Anchorage has. So it has these 2 values here that match our own value. We have up to 5 values here that don't, and it could be for any reason, missing message, or North Dakota was failing, sent wrong data. All of these values are different than the ones we got from Hawaii and Virginia. But there are 2 things here. One is the faulty value. In this case, worst case scenario, they're all isolated to 1 node. North Dakota has touched all these faulty values. And then when it comes to Hawaii and Virginia, not only do they give us the same value, but the value was corroborated because Virginia sent us Hawaii's value, and Hawaii sent us Virginia's value. So we had this robust assurance that they do actually have these values. So from a Anchorage point of view, it's got 2 correct values and then 1 improper value. So Anchorage is going to say, well, I'm going to go with the majority rule on this one. It's a 2 against 1. So I'm going to say majority rule wins. So their value is correct. I agree with their value. So we have agreement between all 3 of us. And now that we have agreement between all 3 of us, I know that I have shared awareness. I know that I'm done with this round. I am ready for the next round. And all the nodes know that. So each node has isolated the other nodes. they've corroborated the correct result. They've isolated the fault, and they know that hey, this is I've got correct agreement. I've got all of us have correct agreement, and it's at this point when they know that they all have the correct agreement that they all know that they all have shared awareness. So all the nodes, even in the presence of this massive fault, know that this process is done. This is a correct data point shared between the team. I can stop, update my value to this data point, and now I can repeat the process and move on to the next one. So there's two important limitations of this solution. So one is your faulty nodes have to be less than 1/3 of the total nodes, and it's usually written like this. So in this case, we have one faulty node and 4 total nodes. 3 times 1 is 3. It's less than 4. So if we had 2 faulty nodes, we would have 3 times 2 is 6, which would not be less than 4. So this wouldn't work. And also you could just see visually, if we had 2 faulty nodes, we couldn't get the majority rule. We wouldn't know that we're in agreement, and we wouldn't be able to reach the shared consensus. And also, theoretically, again, this would work, but this requires an enormous amount of messages to be sent back and forth. So, in each round, each one of these rounds requires n squared number of messages to be sent. And since you're going to do the same number of rounds as you have nodes, it's not n to the cubed. It's not that bad, but it's like just shy of it. So it's an enormous amount of messages that have to be sent back and forth. And for all intents and purposes, it's considered not practical for computers to do this protocol. Theoretically, it could still work. So in conclusion, the Byzantine generals problem just takes the widest and possible interpretation of what can go wrong, what is the worst case scenario inside of a distributed system trying to work together. So in this case, with this problem, the hardest obstacle is the fact that a node, during the process of crashing or failing or whatever, can somehow send 2 wrong and different values, 2 or more wrong and different values to its teammates. So the problem is asking this question is, how can we achieve this end state given this significant challenge?